Any of a class of violently exploding stars whose luminosity after eruption abruptly reaches many millions of times its normal level is referred to as a supernova, plural supernovae or supernovas. The word nova, which means new in Latin and refers to one sort of exploding star, is where the word supernova originates. In numerous ways, supernovae and novae are similar. Both exhibit a strong, quick brightening that lasts for a few weeks, followed by a gradual dimming. They exhibit blue-shifted emission lines in their spectra, which suggests that hot gases are being blown outside. Contrary to nova outbursts, a supernova explosion is a catastrophic occurrence for a star that effectively puts an end to its active, i.e., energy-generating, career. When a star goes supernova, significant portions of its substance, about equivalent to the mass of several suns, may be blasted into space with such an intense outpouring of energy that the exploding star is able to outshine its home galaxy. Cosmic rays are also released during supernovae explosions, along with vast quantities of radio waves and X-rays. Gamma ray bursts and supernovae have occasionally been linked. The Earth and other heavy elements that make up the solar system are also released into the interstellar medium by supernovae. The abundances of the heavier elements are more than expected, according to spectral investigations, which suggests that these elements do actually form during the explosion. A supernova remnant's shell keeps growing until it completely disintegrates into the interstellar medium at a fairly advanced stage. Earlier supernovae. Prior to the early 17th century, just 7 supernovae are known to have been observed. The most well-known of them took place in 1054 and was spotted in one of Taurus' horns. The Crab Nebula, which is made up of luminous gas ejecta shooting outward in an erratic pattern and a rapidly spinning, pulsing neutron star, known as a pulsar, in the center, is the visible afterglow of this explosion. Chinese and Korean watchers captured the supernova of 1054, and certain rock paintings found in Arizona and New Mexico implied that southwestern American Indians may have also witnessed it. It was extremely bright and persisted for weeks. It could be seen during the day. From Earth, notable supernovae may have been seen in 185, 393, 1006, 1181, 1572, and 1604. The first supernova was discovered on the morning of February 24, 1987, by the Canadian astronomer Ian K. Shelton while working at the Las Campanas Observatory in Chile. It was the closest and easiest to detect of the hundreds of supernovae that have been documented since 1604. This object, known as SN 1987A, was previously quite faint, but it quickly increased in magnitude to 4.5 and became visible to the naked eye. The recently discovered supernova was situated in the Large Magellanic Cloud, some 160,000 light-years away. It was instantly the focus of intense observation by astronomers in the southern hemisphere, and the Hubble Space Telescope observed it. The brightness of SN 1987A peaked in May 1987 at a magnitude of roughly 2.9 and then gradually decreased over the ensuing months. Supernovae types. Depending on how they explode, supernovae can be categorized into 2 major categories, Type 1 and Type 2. Type 1 supernovae differ from Type 2 supernovae in that they have no hydrogen lines in their spectra and grow roughly twice as quickly. They may also be up to 3 times brighter than Type 2 supernovae. Supernovae of Type 2. An extremely large star, a population 1 star, with at least 8 solar masses that is towards the end of its active lifetime serves as the parent of the so-called classic explosion, which is connected to Type 2 supernovae. Only spiral galaxies exhibit them, and they are frequently found close to the arms. The star has up to this point in its evolution been illuminated by the nuclear energy generated at and near its core during the process of pressing and heating lighter elements like hydrogen or helium into progressively heavier elements, which is known as nuclear fusion. However, creating materials heavier than iron takes energy rather than producing it. As a result, an iron core is formed at the center of the aging, heavyweight star. When the iron core gets too big, it loses the ability to support itself by fending off the powerful pull of its own gravity with the explosive surge of internal fusion processes. The core consequently disintegrates. If the core is smaller than 3 solar masses, the core will continue to collapse until its constituent nuclei and unbound electrons are crushed together into a solid, rapidly spinning core. Neutrons, which make up practically the entire composition of this core, are compacted into a space that is barely 20 kilometers, 12 miles broad, but has a weight equivalent to many suns. On Earth, a teaspoonful of this incredibly dense substance would weigh 50 billion tons. Those things are referred to be neutron stars. When material from the star's outer layers falls in and bounces off the core, which has stopped compressing and now abruptly exposes a hard surface to the infalling gases, a supernova detonation results. The star's outer gaseous layers are blown off by the shock wave created by this collision, which propagates outward. The original mass of the star determines how much material is blasted outward. The core collapse is too strong to create a neutron star if the core mass is greater than 3 solar masses. Instead, the exploding star is crushed into an even smaller and denser body known as a black hole. The gravitational pull of a black hole, into which matter falls, is so strong that not even light can escape. Since a large portion of the falling star's envelope either bounces back from the momentary development of a spinning neutron core or misses passing through the core entirely and is spun off instead, the entire star is not swallowed by the black hole. Supernovae of Type I. On the basis of their spectra, Type 1 supernovae can be split into 3 subgroups, Ia, Ib, and Ic. Although it is still unclear exactly how Type 1 supernovae of the Ia variety come to be, it is generally accepted that these explosions occur in binary systems with a relatively massive star and a white dwarf, with material moving to the white dwarf from its bigger companion. If the influx of material is sufficient to increase the white dwarf's mass past the Chandrasekhar limit of 1.44 solar masses, a thermonuclear explosion will occur. In contrast to a conventional nova, when there is less mass movement and only a surface explosion happens, an Ia supernova explosion is thought to totally destroy the white dwarf. It produces radioactive materials, particularly nickel-56. Significant amounts of energy are released during the decay of nickel-56 to cobalt-56 and then from that to iron-56, which may account for the majority of the light visible in the weeks following the explosion. Given that they all have the same luminosity, Type Ia supernovae are helpful tools for studying the structure of the cosmos. One can gauge the universe's expansion pace and how that rate changes over time by analyzing the apparent brightness of these objects. Using this technique, dark energy, a repellent force that makes up the majority, 73% of the universe, was found in 1998. Type Ia supernovae that erupted during a time when the universe was only 2/3 the size it is now were fainter and hence farther distant than they would be in a universe without dark energy. This suggests that due to dark energy's current dominance, the universe is expanding faster than it did in the past. The early universe had very little dark energy. According to theory, double star systems with closely orbiting stars are where the majority of novae are thought to form. One of the stars in this system, which is also known as a near-binary star, is an old red giant, and the other is an old white dwarf. In some situations, the red giant enlarges into its companion's gravitational field. Because of the white dwarf's powerful gravitational attraction, hydrogen-rich material from the red giant's outer atmosphere gets drawn onto the smaller star. A nuclear explosion that results in the release of hot surface gases on the order of 100 to 10,000 the amount of material in the Sun takes place when a significant amount of this material builds up on the surface of the white dwarf. The prevailing idea states that after the explosion, the white dwarf calms down. Nevertheless, the flow of hydrogen-rich material instantly resumes, and the entire process that caused the outburst repeats itself, causing another explosion to occur 1,000 to 10,000 years later. However, recent research indicates that such outbreaks might occur more frequently, perhaps every 100,000 years. According to the explanation, a nova outburst separates the two stars in a binary system, blocking the flow of matter until the two stars move in close proximity once more after a significant amount of time. This is all for today. Thank you for staying with us. Don't forget to like and subscribe our channel. See you soon.